That's there. One. Right. I think you're live in both. You are. Have a good show. Monitoring. Oh, did you get punch?
No. Get Dashel. Get that Dashel.
Get that little punch boy. Hey, punch master.
Hello. All right. It is Math Thursday. Math Thursday. All right, guys. So welcome to Math Thursday. We will get into some math problems here soon. So, I've been doing a lot of geometry lately with my students, but let's do something that let's do let's start off with a little bit of a percent. Okay. All right, CapCut editing, you need help. You need help with what? Okay, so those of you who are just joining us, we've got, so let's see, with like the table where you have to find the missing numbers. Ooh, CapCut. Let's see. CapCut, do you mean like an XY table with like a function chart? There's a lot of different ways that you can do tables with missing numbers. Okay, of does usually mean multiply, yep. All right, guys, so work this problem out, and when you get an answer, put it in the chat, and we'll get into it in just a couple minutes. Also, if you have any questions, any content that you want to go over, pop it in the chat and we'll try to get to it. We tend to stay between like pre-algebra and like algebra 2 concepts. But if you have anything that's in pre-calc or above, you can put it in the chat and there might be some people that can help you out. We have a great community here. So let's get into that. Let's see. Christian Guy Cat over on YouTube is saying, why is math important? Math is important because, I mean, math is part of everything. Math teaches not just like the numbers. It's not just about the numbers. It's about problem solving. It's about perseverance, right? It's about looking for patterns and things like that. So it's everywhere. It's everything. Okay, so CapCut, if it's 7th grade math, you're probably talking about it like a function table. But yeah, look in maybe your homework or something that you have, and we can see how to help you out with that. Okay. But everybody else who's here, welcome. So if you have any questions or any content, maybe you have a test coming up. Some of you might be getting ready for midterms or finals. So pop it in the chat if there's anything that we can get into. We'll get into it. All right, so 42 is 30% of what? So this is going about with the percentages. So I know a lot of students like in 7th grade really focus on this. A lot of my 7th grade students that I work with are working in percentages right now. And so there's two major ways of doing a percentage problem. And that would be using either the equation or using the proportion. So the proportion is usually pretty straightforward with students because it's always set up the same. So you have a proportion between the part and the whole, and that's going to equal the percent over 100. So a lot of students really like this because they've already looked at they've already worked through with proportions and all of that. So they're comfortable setting those up. And also it just makes a really nice pattern for that. So usually when you're talking about this of, right? When you're talking about a percentage, this of is linked to the whole. Okay, so 42 is 30% of the whole. So 42 is the part. The whole is X. And then we've got 30 over 100. Okay. So now what we do with a proportion is we're going to cross multiply. So we do 42 times 100 equals X times 30. So we have 4,200 equals 30X. We divide by 30, divide by 30. And what do we get? We get 140 is our X value. Okay. Yes. Ugh. Let me go ahead. I didn't grab my calculator ahead of time. Out of there. Okay, let's see. Uh-oh. Oh, here it is. All right, let's see. Okay, proportional ratios. Okay, yep, so proportional ratios. So when we're talking about proportional ratios, so let's go ahead and get into that because that's very closely related to, what we were just doing with proportions, right? So when you're talking about a proportional relationship, okay, a proportional relationship is where if we just use like X and Y, a proportional relationship is where you have that the value for Y equals K times your X value, okay? That K is your constant of proportionality. So that's what you're gonna be multiplying your X values by to get your Y values, okay? So if you were to, so usually when you're looking at these tables, these proportional tables, and again, this is usually like 7th grade math, maybe 6th grade math, but what we're looking at is we're looking at how these are related, okay? So if you have something like, ooh, that's a terrible line. Oh my God, this is getting worse. Okay, I'm just gonna stop there. Okay, so in a proportional relationship, when X is 0, Y is 0. If that's not true, it is not a proportional relationship. It could be a linear relationship, right? But it's not proportional. So you've got to have that 0, 0. Now that doesn't help me to figure out the K value, right? But if I have 3 and 4, so when X is 3, Y is 4. Okay. Hi, Mac. How was Disney today? Not jealous at all since we got another inch of snow. Okay. So this would be 6 and 8. So then if this one here, right, if we keep going, right, we could do like 9 and 12 or anything like that. And you can see that this one is increasing like +3 and this one's increasing like +4. Mac, you did really well on your quiz. So check out your grade. You did well. Okay, so when we're looking at this, what we're looking for is, what am I multiplying my x by to get my y value? So we're going to plug in some values that we know. We know that when y is 8, our x value was or is 6. So k times 6 gives me 8. So in order to get k by itself, I'm going to divide both sides by 6. And what I get is I get 4 over 3, because 8 over 6 is going to simplify to 4 over 3, which is my k value. So once I figure out what that constant is, then I can go through and I can just kind of follow along with the pattern and go along with that to fill in any missing information. So eventually what you'll get to is you're going to talk about this being the slope. So that constant of proportionality is something that we call the slope. And that is going to be, that's the same thing as like the rate of change. Okay. So yeah, I see a lot of people that are talking about like with the y equals mx plus b. So this question started out with just talking about constant of proportionality and just proportional tables. Okay. So, but that's kind of to give you an idea of how to do it. So with your filling in the tables, right? So if you're filling in the table, oh, no. Okay, so it depends on if you're given the constant or not. Okay, so if you're given the if you're given the constant or not, it kind of changes things. But even if you're not given the constant, as long as you have one like pair together, you can kind of figure out how it goes, right? So let's see. All right, so going from this, well, so this constant of proportionality stuff is really primarily like 7th grade is when you start to really get into those a lot. Okay, so let's see. Okay, so if we have x and y, and let's say we've got 2 and 4 and 9, and this is 64, and this is 80. Okay, and if you're trying to fill in the missing parts, okay, so if you're trying to fill in the missing table, Shravan, this is not the place for Calc 2, but if you have a specific question, you can pop it in the chat and there'll be some people that can help you out with that. But we tend to stick between like pre-algebra and algebra 2 on this channel. Okay. Oh, here's my mouse. Oops. Okay. All right, so finding the amplitude, period, and the frequency of sine and cosine functions. Quincy, I'll see if we can get into that, but it's kind of hard in this format to get to, there are some things that are just difficult for me to convey and put up here, but I'll see if we can get to that. All right, so percent error and factoring and solving polynomials. Who was asking for polynomials? Holland. Solving and factoring polynomials. Of any degree or just quadratics or what? That gives me an idea of where to go with that. Cooper, I did not major in mathematics. I actually majored in biochemistry. So I can't really help you with that question. All right, so what we would look for is we're gonna look for our constant, right? Or what we can also look at is our constant of proportionality is how you're multiplying to get the other value, right? Like, yes, it's y equals k times x, but what we can also do is we can see, okay, 4 times what gives me 64? So to figure out 4 times what gives me 64, I do 64 divided by 4, and I get 16. Okay, so if I need to go backwards, okay, like go from y to x, I would divide by 16. Okay, so here for 9, I have my x. So I'm going to say times 16. So 9 times 16 is 144. Now up here with 80, well, actually, I could do the same thing with 2, right? So 2 times 16 is going to give me 32. And then over here, when I have this one, 80, I would divide by 16. So 80 divided by 16 is 5. So my constant, if I do y equals k times x, my constant is actually going to be 16. Okay, so my y equals 16x. Because what am I multiplying x by to get y? 16. Okay, so yep, so k is 16. All right, so percent error. Somebody was asking about percent error, which again leads right in, is very nice transitioning from the opening problem, which was just finding the percent. So the percent error is sort of like the same thing as like percent change. Okay, it's basically like how far were you off in your experiment or in your data collection or something like that, right? It's measuring the accuracy of your thing. So the measured value compared with the actual value. Okay, so what you do is you would take your measured value. So I'm just going to say measured minus your actual. Okay, or like expected or exact or something like that, right? So the percent error is measured minus actual divided by the actual value. Okay, this could also be your measured minus your expected divided by your expected, right? And then you would do that and then you would multiply it by 100 to get the actual percent. Okay, so you could do the absolute value if you just care about sort of like the exact distance away from the actual value that you got or your expected value. But you could make it positive or negative. You could take away that absolute value to talk about a positive percent error or a negative percent error, because that would tell you which direction your error was falling, okay, or following. Falling. So that percent error or percent difference or relative error, there's lots of different ways to calculate it. You might see like experimental minus actual over actual, or experimental minus expected over expected. Those are all different things. This is a really, really, really important statistical analysis when you are talking about like accuracy, precision, all of that kind of stuff. Okay. All right. Okay. So factoring and solving cubic functions and I. Okay. Ooh, you know what? Let's get into imaginary numbers. Let's talk about them. So imaginary numbers, and we will get into, we'll look at solving, factoring and solving cubic polynomials. Okay. Imaginary numbers. I know, it's always kind of ridiculous when you first start imaginary numbers because everybody sort of freaks out. Once the initial shock of like, oh my God, there's imaginary numbers, once that wears off, they're not so complicated, right? Okay. So let's look at, okay. Imaginary numbers are really easy to look at when we talk about just like a quadratic, okay? So with a quadratic, you have something like this, right? Your roots or your zeros or your solutions are these 2 points, right? That's where they are. That's where they're going to cross. Okay? That's where they're crossing the x-axis, right? It's like -3 and like negative, I don't know, we'll call it 9.5. Okay, so our solutions here are -9.5 and -3. Okay, those are our solutions. Those are our roots. That's where y equals 0. If you have something like this, okay, it doesn't cross the x-axis. So there are no real roots. But that doesn't mean I can't solve them, because mathematicians decided, you know, if we could just work with these negative roots, like, you know, like square root of a negative number, if we could work with those, we could still get these imaginary roots. They're just not really there on the graph. So we have imaginary numbers, okay? So when we are looking at something with an imaginary number, so let's say you end up with like square root of -9, okay? So square root of -9. So when you first learn square roots, you learn like, woof, you can't do a square root of a negative number. You can't do a square root of a negative number. You can't do a square root of a negative number. That is true if you're only talking about real numbers. But again, when we get to this point, mathematicians just didn't want to stop there. They wanted to keep going. They wanted to keep working with it. So what they did was they said, okay, you know what? We're going to use this I, which stands for imaginary, okay? And it's the square root of -1, okay? I don't know if it actually stands for imaginary. I assume it does. I don't know. But we've got I equals the root of -1. So now the root of -9 is going to actually be, so we can break this up into the square root of -1 and the square root of 9. Okay. Now the square root of -1 we just said is I. Square root of 9 is plus or minus 3. So the square root of -9 is actually plus or minus 3I. So all an imaginary number is it's a square root of -1. That's it. That's the whole secret. That's all it is. Okay, so when you're working with these roots, you just take out that negative and slap an I on it, and then we look at the root right there. That's it. Okay, I'll add permutation and combination to the list because they are confusing. Oh, okay. So now when we're looking at these, right, the real roots can be, or sorry, not the real roots, but the roots can be imaginary. They can be imaginary numbers. Okay, So let's get into factoring and solving cubic polynomials. Where did all of my boards go? I just cleaned off a bunch of boards. I need more whiteboards. Marker board people, I know you're a Michigan company. I would love to partner with you. Just let me know. Okay, so let's do, I just want to find, okay. Okay. I just wanted like an easy one to just give me a problem. Ugh. Okay. Just wanted a couple of cubic equations that we could solve by factoring. Okay. Okay. So here, let's just start with just a cubic polynomial. Okay. So we've got x cubed minus 4x squared minus 9x plus 36 equals 0. Okay. Oh, let me catch up on the chat. I missed some things. Oh, Jack, I don't use delta math. I don't know. I'm not very well versed in delta math. Yeah, Naomi, I'm with you. I don't do delta math. I don't know. I know a lot of people really like it, but I just don't have a lot of experience with it, I guess. Okay, so here we go. We've got this polynomial. Okay, polynomial means that it's many termed. Okay, so it's got many terms here. So we've got x cubed minus 4x squared minus 9x plus 36. First thing I'm going to do, I've got 4 terms. That means I can factor by grouping. So factoring by grouping, I'm going to take this half and I'm going to take this half. Okay. X cubed minus 4x squared. I can take out an x squared from both of those. And what's left behind is x minus 4. Okay. Now here I'm looking at minus 9x plus 36. Now since that first term is negative, I'm going to factor out a negative there. And I want what's left behind from here to match up with this one. So I'm going to take out a minus 9. And that leaves me with x minus 4 again. Equals 0. So now these are the same. And these become my other binomial. So I have x squared minus 9 times x minus 4, and that gives me 0. Now here, now that I've got it set to 0, now I've got it all factored and nice. Now I can just start to solve. I can use the zero product property, which means that if I've got things that are multiplying together to equal 0, in order for them to multiply together to equal 0, one of them has to equal 0. Okay? So in this case, when I've got all of these things, I wonder if you guys can see my graph. Let me see, hold on. Okay, so what this polynomial is going to look like is it's going to look something along these lines. It kind of goes up and then it dips back down and then it goes like that. Okay, so in this case, this equals 0 part is when your y value is 0. So we can see from the graph, it's got 3 points where it crosses the y-axis, the x-axis. I said y-axis, didn't I? I might have, I don't know. It's the x-axis, but y is 0. So we've got 3 spots where it crosses that x-axis where y equals 0. So there are 3 values for x that make my y equal 0. So here, if I go back over, I've got x squared minus 9 is going to be the one that equals 0, or x minus 4 is the one that's going to equal 0. Now in this case, I know, because I've been doing this a long time, okay, x squared minus 9. So now I'm going to like set these equal to 0 and solve them. Now if this were not x squared minus 9, I could then factor this some more, okay? But what I know is that I know that if x squared minus 9 equals 0, I know that x squared will equal 9. So I know that x is going to be plus or minus 3 because I took the square root of both sides. Okay. And then I've got x minus 4 equals 0, where x minus 4 equals 0, that's when x equals 4. Okay. So the 3 spots where my quadratic hits that x-axis, obviously this is not drawn to scale, right, are -3, so -3, and then +3 and +4. Okay? That's how I got those values, is by factoring up here. Okay. All right, so let's do one with more complex roots. I wish I could fix it. I don't want it. Okay, I might just have to make my own. Reading on, what are you talking about? Don't get it, please. What? All right, user 155439. Another one like this, another cubic like this. Ooh, Grant, I can definitely do completing the square. All right, I'll do one more cubic. Let me, hold on, I gotta do a couple things. Hold on. No, not that one. Okay. Ooh. Okay. Okay. All right, so let's see. This one should work. This one should work okay. All right, so we've got f of x equals 3x cubed minus 12x squared plus 4x minus 16. Okay, Grant, I will definitely do completing the square. Okay, 'cause I love completing the square. Okay, so let's take a look at this. So we've got this is called a cubic polynomial, right? It's cubic because it's 3. Yep, we're gonna factor by grouping first. Okay, well, first I technically need to set it equal to 0, right? Because that's what I'm trying to figure out. So I'm gonna set it equal to 0. So 3x cubed minus 12x squared plus 4x minus 16. Okay, I'm gonna factor by grouping now. So 3x cubed minus 12x squared. So what I can take out of there is a 3x squared. And what I'm left with is x minus 4. And then over here, I can take out a 4, a positive 4. And again, I'm left with x minus 4. Okay. So I'm just going to flip around kind of the order of this. So I've got 3x squared plus 4 times x minus 4 equals 0. Okay. So now I've got 3x squared plus 4, and that's going to be equals 0. Okay, and I've got x minus 4 equals 0. So I know that x minus 4 equals 0. That's one of my solutions. So one of my roots is positive 4. Beautiful, right? Okay, now 3x squared plus 4. Oh, this is going to actually be really gross. All right, well, let's get into it. So we have 3x squared plus 4 equals 0. You guys asked for imaginary numbers. You asked for complex numbers. So we are into this. Okay. Too late to turn back now. All right. So I'm going to transfer this part onto a different board because we're going to need some more room for this one. Okay. All right. So 3x squared plus 4 equals 0. Let's actually turn this way. Ooh, 3x squared plus 4 equals 0. All right. So again, we did our cubic root, right? We did our cubic polynomial, blah, 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 all the way down. And now we're at this point. We already figured out that one of our solutions is 4. We're figuring out our other solution now, our other root. All right, so 3x squared plus 4 equals 0. So I am going to, because I don't have a linear term, which would just be like x in the middle, I'm going to go ahead and I'm going to solve this using square root property. So I want to get the x squared by itself. So I subtract 4. So now I've got that negative 4 over there. Minus 4. And then I'm going to divide by 3. So x squared equals negative 4 over 3. Okay. I square root both sides. I get x equals plus or minus the square root of negative 4 over 3. Now the square root of negative 4 over 3 is going to be plus or minus, again, I've got 2i on top because I is the square root of negative 1, so that comes out and becomes I, and then the square root of 4 is just plus or minus 2 over the square root of 3. Okay. Now I can't leave it like this. I've got to rationalize the denominator, right? Ooh, Justin, I think you've got it. I got to rationalize the denominator. So I'm going to bring that over here. I'm just going to bring it over here. I've got 2i over root 3. So to rationalize the denominator means I don't want that radical in the bottom. So I'm going to multiply it by root 3 over root 3. This is just multiplying it by 1. And I can just multiply it by any version of 1 as long as it's the same thing on top and bottom, whatever's going to help me out. Root 3 times root 3 is just 3. Right? Square root of 9 times the square root of 9, that's 3 times 3, which is 9. Square root of 5 times square root of 5 is 5. Square root of 3 times square root of 3 is 3. So we've got 3 on the bottom, and then we've got plus or minus 2i root 3 on top. I can't simplify that, but if I could, right, if this were like a 6 over 3, I could simplify that down. But that is going to be my other set of solutions. So my solutions for this whole problem were, if we go back here, right, we've got 4, and we have plus or minus 2i root 3 over 3. So there we go. There's a cubic polynomial. It's just going back to factoring by grouping, and then you're solving this quadratic. Okay. Okay. We did imaginary numbers. Okay, completing the square, then permutations and combinations. All right. So completing the square, I love completing the square. Okay, completing the square, you can do this to solve quadratic equations or quadratic functions. Okay. So quadratic equations and quadratic functions is, oh, Caleb, if you're just joining us, this is primarily like algebra 2 kind of stuff that we're into tonight. Sometimes we're more into pre-algebra, sometimes we're more into geometry. It just kind of depends week by week, but if you have a specific question, let me know. Okay, so let's do x squared plus 6x minus 4 equals 2. Okay. So looking at this, okay, first thing I want to do is I'm going to make it equal to 0 because that's usually the first step in any time that you're trying it. And I'm coming at this as if you don't necessarily know how to complete the square, okay? But you're just learning quadratics and your teacher says like, just make it equal to 0 and then go from there, okay? Because if you're gonna use quadratic formula, it's gotta be equal to 0. I can't use square root property because I have a linear term, I have an x, okay? So here I check to see, can I factor this? Okay, so I can't factor it because -6, so to factor it, I would need two numbers that multiply to -6 and add to +6. And -6 would really just be 1 and 6 and 3 and 2. And I can't get those to add together to be +6. So I can't factor it. But I do notice that this is a 1 and this is an even number. I can do something called completing the square. So what I'm going to do is I need to think about what's called a perfect square trinomial. Okay, so a perfect square trinomial is something like if you had like x plus 2 square. Actually, I'm not gonna use 2. I don't like using 2 because it's hard to tell if you were adding them or multiplying them. Okay, that's a little tip for teachers out there. So x plus, let's do 5 squared. So x plus 5 squared, if I do x plus 5 times x plus 5, that's going to give me x squared plus 10x plus 25. I know this is a perfect square trinomial because half of this value squared is this value. Okay, so half of this squared is this. And that half becomes that part right there. Okay, yep, so it's a squared plus 2ab plus b squared, exactly. So if I translate this up to here, I go, okay, well, 6 is an even number. 6 divided by 2 is 3. 3 squared is 9. If that were plus 9, this could be a perfect square trinomial, and then I could just take the square root of both sides. But it's not, it's minus 6. But in a perfect world, if it were x squared plus 6x plus 9, I could just, boop, do this. Hi, Malik. I could do half of this squared, because half of this squared is 9. So this could become x plus 3 squared. Okay. So I can just kind of, this is called completing the square. So even though it's not a perfect square when I start out, I can actually make it a perfect square. If I just add, in this case, I'm going to add 15. That makes that 9, because negative 6 plus 15 is 9. So I'm going to add 15 over here. So now that gives me this here. So by adding 15 there, I have now made this a perfect square trinomial. I'm just going to change this to black because it's now this is the point that we're at. Okay. So now I have made this a complete square. Okay. So I got the 9 because half of 6 is 3. 3 squared is 9. Okay. So now what I can do is I can take the square root of both sides. Square root of something squared is just that something. So x plus 3 equals plus or minus root 15. And then I would subtract 3. So my x equals, sorry, I'm kind of running out of room, negative 3 plus or minus the square root of 15. And those would be my 2 roots. Now, I know, right, Jesse? You don't know you can just add a value, but like, that's why I love completing the squares, because it feels a little sneaky, like I'm not supposed to just be able to add a value, but I can. I can just add a value as long as I do the same thing on the other side. Why not, right? It's still the same thing. That's how we solve equations. So why not use it to kind of force it into an easier way to solve that problem? Okay, it's way easier to do this than to try to do quadratic formula, right? I don't like using quadratic formula. It's just messy. And if you can use completing the square or factoring or something like that, I just use those, or square root, I just use those. So yeah, so I love completing the square. So now a little caveat is that when you're completing the square, you don't, let me say this. When you're completing the square, you can complete the square, like, even if it's kind of a messy equation. I tell my students, and for myself too, I only complete the square if this first coefficient is 1 and this is an even number. You can complete the square on anything else. You can complete the square if it's here. You can complete if it's odd. But it gets messy and it's not fun, right? Like, let's keep math fun. So don't do drudgery stuff, right? Try to keep like friendly problems, like completing the square, because that's a whole thing, is like, you've got to be able to have that choice, right? With this problem, I will choose to complete the square. There are other problems where I would never, ever, ever complete the square. Okay, if this were a 3 and this were a 7, I would never do that. Nope, no thank you. I'll just do quadratic formula, or I'll try to factor it, right? If it's not factorable, then I'll just go to quadratic formula. Okay, but let's keep it fun, because this is fun, because this is kind of neat looking, right? You're like, oh, that is really cool. Okay. Okay. So for the empirical rule, I mean, that's you've kind of done it, like the 68, 95, 99.5, you can just sort of, it depends on what you're trying to do with that empirical rule. But basically, like, that's just the empirical rule. Is it's based on standard deviations. So like 68% of your data is going to be within one standard deviation of your mean. And then 95 is going to be within 2 standard deviations, and then 99.5 is going to be within 3 standard deviations. So anything beyond 3 standard deviations is typically it's one way to kind of like measure for outliers. So oftentimes if it's that far away from the if it's more than 3 standard deviations from the mean, you usually kind of toss that data, or you don't use it in your other things. Okay. Multiplying radicals. Ugh, complex zero theorem and rational roots theorem, Justin. I can't get into that here. It's not like completing the square. That's my first love. Okay. Completing the square. Let's see. So Danny with the square root method. I mean, you can't really do the square root method with it. Well, you can do the square root method once you complete the square, right? But before you complete the square, you can't take the square. That's what completing the square is all about. That's really fun. Okay, so Morgan, how do you multiply radicals? So multiplying radicals. Ooh. I have so many things. Secret, yes, I'm only live on Thursdays, but if you want some one-on-one tutoring or anything like that, you can click the link in my bio, my profile, and you can book an appointment and we can go over things. Can you only do it if it's in vertex form? Are you talking about the Danny, what are you talking about? What do you I didn't mean that to come up as rude. What do you mean if it's in vertex form? The square root method for solving a quadratic? Oh, I see what you're saying. Only if it's in vertex form. Not necessarily, because you could do the square root method if it's just like x squared equals 6. You can just take the square root of both sides. So x would be plus or minus the square root of 6. That would be the square root method. But if it's in vertex form, that does make it easier to do the square root method, because you already have that perfect square. Yeah. Okay. Let me see. What was I going to do? Oh, multiplying radicals. Okay. Morgan, multiplying radicals, and then Jaffe, I think. I can't read your name. What does it mean when you say to reflect over the x-axis? Ooh, Finnick. So Finnick with extreme values using derivatives and all that. We usually end kind of like at algebra 2. But there might be somebody in the chat that can help you out with that. Let's see. Okay, so oh my gosh, vectors. We're not getting into vectors. Let's see. Okay. Multiplying radicals. Oh my God, Morgan, I keep forgetting. I'm sorry. Okay, so multiplying radicals. So square root of, let's say square root of 24. We're going to kind of work backwards with this, okay? So square root of 24 is the same thing as square root of 4 times 6, which is the same thing as the square root of 4 times the square root of 6. Now, this is what we use when we're simplifying radicals, okay? Because the square root of 4 is 2. Square root of 6, we can't simplify it, so it becomes 2 square root 6. Now, what's nice is that this actually works in the opposite direction too. So if I'm multiplying radicals, and if I've got like root 3 times root 2, okay, that's going to be the same thing as root of 3 times 2. Now, the reason I'm able to put these under the same root is because they're at the same index, which means like they're both square roots, right? So root 3 times 2 is the same thing as root 6, and we can't simplify that any further. Okay, so some of these you will be able to simplify further, but not all of them, right? So for example, if I wasn't doing 3 times 2, but I was doing root 3 times root 6, that's going to be the root of 3 times 6, which is the same thing as root 18. Now, root 18 is the same thing as 9 times 2. Square root of 9 is 3. Square root of 2 is the square root of 2. So multiplying those radicals, you can stick them underneath the same radical symbol as long as it's the same index, okay? So as long as it's the same root, like square root, cubic root, fourth root, whatever it is, right? You can stick them under the same radical sign, okay? Ooh, Alexa, quadratic formula. User trig. What kind of trig? You got to be a little bit more specific. I probably have time to do one more thing. Okay, so you know what? Let's just stick with the quadratic stuff we've been doing all day, and we'll do quadratic formula. Why not? Okay, so we've been talking a lot about like completing the square roots. We've been doing solving the, with imaginary numbers, all of that. So sometimes you will end up with a quadratic that you can't factor it. You're not going to complete the square, and you can't do square root. So what do? Quadratic formula. The good old standby. Quadratic formula will work for any quadratic equation. Okay, so I have no idea what this is going to end up being, but let's say 3x squared plus 4x minus 10 equals 0. I don't think that's factorable. Okay, so we look to see if it's factorable. So 3 times negative 10 is negative 30. 2 and 15, 1 and 30, 6 and 5. That's not gonna factor. Okay. Oh, so Justin, here's what I'm going to tell. I'm not going to work out a complete circle equation because we're just about out of time. But what you can do is look at the equation for a circle function, use some of the points, like use the center point, and see how you can complete the square to make that square there, right? So completing the square gets that little part that like x minus h squared, I think. Yeah. Oh, yay, Tia, you got an A in your quiz. That's awesome. Okay, so let's go back to this one. So we can't factor it. I'm not completing the square because that's 3. That is 4, but that's 3. Ugh, I'm not going to do that. I don't want to do complete the square on 4/3. Gross. So I'm just going to go through with quadratic formula. Now, quadratic formula, I've got A, B, and C. Okay, so this is A. 3 is my A. Positive 4 is my B. Negative 10 is my C. It's got to be equal to 0. All right, so I'm going to do, so my quadratic formula is x equals, everybody knows the song, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Boop, right there. Okay. Now I just plug it in and solve. All right, this part down here, this b squared minus 4ac, once you get into like algebra 2, you start talking about the different types of roots you can have. This b squared minus 4ac is your discriminant. So that is a value that can help you determine what sort of results you may get or what sort of roots you might find, okay? All right, so x equals negative 4 plus or minus the square root of 4 squared minus 4 times 3 times negative 10 all over 2 times 3. So I just plugged in all my numbers there. I plugged in all my values right from my equation. I have to double board this one. Okay. All right, so we start to simplify. Do not just plug this all into your calculator. Don't do it. You never plug it in right. So we just take this piece by piece. So I've got negative 4 plus or minus the square root. So I've got 16 plus 4 times 3 times 10, which is 120. So I've got 16 plus 120. I'm just going to go ahead and write out 136. Okay. And I'm also going to double check. Whoop. It's been a long day. So 4 squared minus 4 times 3 times negative 10 is 136. Beautiful. Okay. Over 6. Now root 136, can that be simplified? Yes. So 136 is divisible by 4. So this is going to be negative 4 plus or minus. So 136 is 4 times 34. So my 4 is going to come out and become a 2 root 34 over 6. Now this is kind of what I was talking about before when you can simplify all these things. Okay. So I've got negative 4 plus or minus 2 root 34 over 6. So I can simplify all of these numbers here by 2. 1 and 3. So my solution is going to be x equals negative 2 plus or minus root 34 over 3. Okay, if you just stuck that in your calculator, you'd get a big ugly decimal and you would have no idea if it was right or not. So there we go. Okay. Oh, did I want to be a teacher for 20 years? I mean, once I discovered that I wanted to be a teacher, I can't really imagine doing anything else other than teaching. I don't know. All right, guys, it is about that time. Okay. I will be back next Thursday. I know a lot of you have finals and midterms and all sorts of things coming up. So make sure you tune in next Thursday. Send me your questions if you have any specific questions or concerns or anything like that. Go ahead and send me a message. You can check out my profile, click the link, do the stuff. You can book some one-on-one tutoring sessions if you would like. And that's it. I'm out of here. Next week, same time, same place. We do like pre-algebra through like algebra 2, but yeah, and geometry also. So geometry is here also. Okay, so it's 8 o'clock, I guess Eastern, United States. Have a good night, guys. Bye.